Welcome back to Applied Algebra and Trigonometry. Today we're going to be talking about factoring quadratic equations. Here we have the general quadratic equation, ax squared plus bx plus c, where we consider a and b to be coefficients of the variable x and c to be a constant. Now there is one thing that must be true for you to have a quadratic equation in this form, and that is that a cannot equal 0. You have to have some squared term. If a is 0, that term disappears. Here are some equations. They all have equal signs. So yes, they are all equations. So I ask you, which of these is a quadratic equation? There may be more than one. Is a quadratic equation? No. There is no x squared term. It is not a quadratic equation. It is actually a vertical line. Is b a quadratic equation? It's not in the form, is it? But if we can manipulate it to get it into that form, then it is a quadratic equation. So let me do that for you. I'm going to subtract 2x from both sides, and I'm going to subtract 3 from both sides. Now, does it look like a quadratic equation? Yes, it does. Right, there is no b term. It's missing. We have our ax squared, where a is 1, and no bx, and we have -3 for our constant. But yes, that is a quadratic equation. What about c? We can manipulate it too. This time, let's move x squared to the other side and our -4x to the other side by subtracting x squared from both sides and adding 4x to both sides. Is it a quadratic? No, it is not, because as soon as you subtract that x squared from both sides, it disappears, goes to 0, and we have 7x minus 2 equals 0. D, yes, D is a quadratic. Just like number 2, it is simply missing the middle term. Okay, what about E? Is it a quadratic? Yes, it is. Actually, it too is missing the middle term. If we subtract 6 from both sides, we get that. Let's try one more. Is the equation x squared plus 2x equals 0 a quadratic? Yes, it is. Right, there is no constant term there, but that's okay. As long as the first term is there, as long as we have an x squared, we're fine. Now let me ask you a little different type of question. So I've kind of put a dotted line across the bottom. Let me make room for this. My question now is slightly different. Can these concepts be represented by a quadratic equation? The answer in all cases is yes. Projectile motion, electrical current, and forces on a beam. To solve quadratic equations, you first convert to the form ax squared plus bx plus c equals 0, the general quadratic equation. Next, you factor the quadratic expression. The third step is to set each factor equal to 0. The fourth step, solve the resulting linear equations. Number 5, recognize that you have your solution. These are the solutions or roots or zeros of the equation. They are called different things depending on what you want to emphasize about those solutions. And the most important step, number 6, check all solutions. Why is that most important? If you check your solutions to equations, you'll always know whether you got it right or wrong. If the check doesn't work out, you've made a mistake somewhere, probably in your original work, but it could be a mistake in the check also. Either way, it tells you you need to go back and take another look at this so you can get full credit, so you can understand the equation, so you can communicate that understanding to me or to anyone else. So here's our first application problem for these quadratic equations. Projectile is launched with an initial velocity of 320 feet per second. Its height above the ground after t seconds is h of t, so the function of t, which is time, in seconds, equals negative 16t squared plus 320t. When does the projectile strike the ground? We are assuming it's going to strike the ground and not achieve orbit or escape velocity. But at what height is it when it's on the ground? That would be when the height equals 0, right? And the height is a function of time. So when h of t equals 0, the projectile strikes the ground. So let's let h of t equal 0 and solve to find out at what time that is. Let's remove the greatest common factor of negative 16t. That leaves us with t minus 20. Now I take each of my factors and set them equal to 0. The justification for doing that is if negative 6t equals 0, doesn't matter what t minus 20 is. I'm multiplying by 0, so I'm going to get 0. Or if t minus 20 equals 0, it doesn't matter what negative 16t equals. You're multiplying by 0 to get 0. And we solve these equations to get t equals 0 and t equals 20. So at time equals 0, is that a possible time? Yes. That's the time at which it is launched. So it's not really when it's going to strike the ground. So we're going to exclude that one. And we're going to say that the projectile strikes the ground after being launched at time equals 20 seconds. If you are given units in the problem, you must report units in your answer and make sure you report the right units. Avoid engineering disasters. Okay, here's a theoretical example. Now, I'm going to go ahead and tell you this is a quadratic. We just have to manipulate it to get it into the form of a quadratic. So first thing I'm going to do is distribute, because I have a t trapped inside those parentheses. That'll give me 43t plus t squared equals 9 minus 9t squared. Okay, I like positive t squared, positive leading coefficients whenever possible, so I'm going to add 9t squared to both sides. And that will give me 10t squared plus 43t equals 9. Now I just need to move my 9 to the other side by subtracting it, because that gives me the general form of a quadratic equation. All of it set equal to 0, and now I need to solve the equation. There's my big organizational X with AC above it to remind me. I'm going to need to multiply 10t squared times negative 9, and that will give me a negative 90t squared. I want the factors of negative 90t squared that add to give me 43t. Okay, so thinking about that a little bit, I come up with 45t and negative 2t. The larger one is positive because the sum I'm reaching for is positive. See, you can't forget anything in this course. It keeps coming back around. So I have 10t squared plus 45t minus 2t, because those combine to give me 43t, minus 9 equals 0. Now I'm going to factor by grouping. And I'm going to go ahead and include that negative 2 with my t. So I'm adding the quantity negative 2t minus 9. All right, pulling out the greatest common factor here. 5t times 2t plus 9 and minus 2t minus 9. Nothing in common except a negative 1. And when I factor that out, I'll get 2t plus 9, which gives me exactly what I wanted, a common factor in each of those terms. So I factor out the greatest common factor from those two terms, leaving me 5t minus 1 equals 0. I have now completely factored the quadratic expression. I'm now going to set each of these, and I've kind of run out of room here. I'm going to do it over here and over here. And I go through the steps of solving these to get t equals negative 9 halves and t equals 1/5. But now I need to make room to check these. Please remember, I suggest everywhere there is a variable in your original problem, you first put in parentheses and then go back and fill in the value of your variable, because in cases like this -9/2, it's really easy to drop that negative if you don't have a space reserved for it. I'm going to step quickly through the checks. Just pause the video if you need to see things in depth. And I'm almost done. And there, this shows that I have a correct answer in t equals -9/2. You can get really strange, crazy things on either side of the equal sign, but as long as they are equal, you're fine. But I'm not done. I have to check the 1/5 also. In the same way, I put in my parentheses first, and now I'm going to go back in and put in the value of t. Now I start working through this. Fractions are fine. You can get used to working with fractions. And you wondered why we wasted all that time in multiplying and dividing and adding and subtracting fractions. Oops. This is why we did it, because it's useful. And there are my two answers. I've confirmed it. I was not given any units, so my answers are unitless. By the way, I'm putting some of the harder problems in this video, so you'll see how to do them. So don't worry, they aren't all this difficult. So, all right, we have here some fractions, we have variables, we have an equation, so we should be able to solve this somehow. So let's find our least common denominator, remembering that any number can be made into a fraction by dividing it by 1. What is our least common denominator? Well, the prime factorization of the first factor is 2, and of the second factor is x minus 3, and of the third factor is, well, 1. We don't even really need to write that. So there's our least common denominator. Now, we could go through the process of converting all of those fractions to equivalent fractions that have that least common denominator. But here's something else you can do. If instead we spread things out just a little bit, and to keep things balanced, we multiply both sides by 2 times x minus 3, because the golden rule of algebra says do unto one side as you would do unto the other. And multiplying this side by 2, the right side, by 2 times x minus 3, I could put it over 1 to make sure it's a fraction, but we don't really need those to be fractions on that side of the equation. Okay, and on the other side, we're multiplying the whole side by our least common denominator. That means we have to multiply each term by the least common denominator. And these are fractions, so I'm going to put my LCD over 1. And now I can do some canceling. And in fact, this is exactly why we use this technique. All of your denominators should cancel. If they don't, you have a mistake somewhere. So I'm just changing the order here a little bit, since it's multiplication in that first term. Plus 2, that's all I have there. Equals 6 times x minus 3, because I multiplied 3 times 2. And now here I have x squared minus 3x plus 2 equals 6x minus 18. Now I'm going to move everything, over to the left, because on the left I already have an x squared that is positive. There we go. Now I have an expression that I can factor. The factors of 20, positive 20, that add to be -9 are -4 and -5. I set each of those equal to 0 and solve. So my answers are x equals 4 and x equals 5, but not so fast. I have to check first. And I have to check in my original equation, which is a little bit difficult to see right now. Just a moment. And with the magic of video, Boom. There, I'm getting back to the original equation. And everywhere there is an x in the original equation, I am going to put parentheses. Plus 1 over parentheses minus 3 equals 3. And I'm going to slip a 4 into each of those spots. Let's see, 4 divided by 2 gives me 2. I have 2 plus 1 over 1 equals 3. So that's 3 equals 3. That one checks. What about 5? Is it going to check? 5 divided by 2 plus 1 over, it's going to be 5, minus 3. So 5, 5. I have, 5 halves plus 1 half equals 3. Ran out of room a little bit. Let me move this up. Okay, 5 halves plus 1 half is 6 halves. 6 divided by 2 is 3. This one checks as well. Both of them check. These are my answers. So if you have fractions in an equation that you're working with, feel free to multiply both sides of the equation by the least common denominator, but it must be the least common denominator of every term on both sides of the equation. I highly recommend this. It's a very useful technique. And that's all I have for today. Everything we've done here is based upon something we've already done. Factoring quadratics, solving linear equations, substituting values into an expression and evaluating. You know how to do it. Go to it.